Play here. Okay, so this is a special late night edition. Normally we do 4 to 5. We may switch next semester to actually give you guys an hour, the virtual kids that is, which means that you'd have to, I take roll. That's the problem, is that's going to be the problem. Is how do we deal with roll? Anyway, let's not worry about that tonight. Okay, so I'll try and make this as quick as I can. Let me share the screen. One thing that we don't have to worry about on Zooms is fire drills. Daggone fire drill. Messed up my third hour. Okay, so this is for Wednesday. Let's see if anything else here. I am just about, I'm probably at 95, 96% now, so Canvas is starting to act a little funny. I just got to get through next week, right? Really, 2, 3, 4 more days, and then the rest is just tests and that kind of thing. So I think I can get through, but we'll see what happens next semester. Today's the reason why I wasn't here, but tomorrow, just letting you know, if you're going to be around, even if you're virtual and you want to come, probably not first hour, I'd probably come third hour. We'll probably start heading out. You can meet us at Harv Collins if you want. We're not doing a whole lot there, to tell you the truth. We're just trying. There's a saying called nullius in verba, and it's Latin. It means not by word of mouth, and that was the motto of the Royal Society. I have this painted above my door. So Newton and the boys, said, "Hey, we're tired of being, as all scientists coming from Mount Olympus. I mean, we want to get our hands dirty." So that's where we're going to the stadium tomorrow. Because I can tell you that G is 9.81, but we need to go prove it for ourselves and go see how you get that, rather than just by word of mouth. Okay, so that's why it's worth going to the stadium. And I've got to go to the stadium tomorrow because Friday is going to be rainy and really Monday is too late. So anyway, the point is, if you're going to be around tomorrow, wear your coat. Okay. We played I Spy in the room, looking for the nose, which they found. Black and Blue is due tomorrow. So it's 1 o'clock in the box or 6 o'clock on my porch if you're going that route. And I'll extend the courtesy to that in-class kids, in-person kids, turn to my porch if they have to. Here's what I handed out today, and this is on my porch. It's just, I got like 10 copies out there in case you didn't want to print it off. But this was on PDF last night. We talked about it a little bit in class. Remember, I'm trying to mimic what happened in the 3 classes. So yes, you'll have to do that. I mean, you're going to have to, remember we talked about this when it first came out, you're going to have to know the beautiful patterns. So there's about, if you count it up, there's 50 things you got to know about that set of 10 graphs, but you have to have it memorized. So 50 things. But if you know the pattern, like if I told you, you have to memorize 26 letters, and then like, or I'll say, hey, tell me the alphabet. And you say, okay, I'll tell you the alphabet. Here it is. It is S. It is M. Let's see, there's a V in there. There's an E. So if you try to come at it that way, you don't. You do it, there's a pattern, A, B, C, D. So same thing here. There's a pattern to this. Remember that main, the diagonal pattern. And so you're looking for, that's how things are similar. All right. Anyway, that's in your notes. So this is the current take-home test. And there's some questions about that and questions about graphs in general. And then we have this one. This is like, we've done a couple of these. If you go back and look at the old wrap-up videos, and I know I have 2 or 3 silent help videos on this stuff. And I'll put those, I need to remember, now that's getting close to the end of the pack, I need to start putting keys up and put up these help videos, because I made them. There's like 220 videos on the, if you just go look at playlists, you'll find this probably under Orange Trios or something. or vectors. It's also vectors. It's a good, this kind of problem number 8 is a good segue between trios and actual going into vectors like we're doing right now in class. Okay. Also, there is a derivation on this test for next Wednesday, this 200-point test. This, you're deriving the first orange, the second orange. And so the question that came up today was, well, does that mean that we'll have the same, we'll have to know the second orange for the test? How about this? I will literally flip a coin when I'm writing the test the night before, on Tuesday. I'll flip a coin, and that'll tell me whether it's going to be the second or the third. And I promise you, if I say it, I'll do it. I'll flip a coin, 50-50, whether it'll be this one or the third one. All right. So I don't know. But this one definitely is the second one. So then 10, 11, and 12, there's a shout out to Chuck Yeager there on number 11. But 10, 11, and 12, those are your orange CL Deepa. Also, really, 15 is also CL Deepa. But let's see, 13 is good old Girl in the Jeep. 14 is the bullet in the barrel. And then 15, you can't have a test without a gold standard. So there's a gold standard with the asteroid coming in. So similar themes to what we've done in class. And then you might ask, well, wait a minute, if we've covered all this. I mean, are you saying that the test on Wednesday before break is just going to be all the stuff we've already covered? Yes, in addition to what we're going to cover, what we covered today, like vector stuff. But I'll put an addendum on there. I will tell you, I'll give you plenty of heads up, but hey, also know this, this, and this. Know how to do this, know how to do this. And that'll go into the test as well. But I ran out of room, to be honest with you. Okay. Now, go on the Facebook group. You can come on my lunch. You can come on my room anytime at lunch. But go on the Facebook group and like for especially virtual kids, and I've already had, I think Io was asking questions about some of the problems already in the take home, so that's good. So you can help each other if I'm not around. I'm busy these days with the Ask Me tutoring, and tomorrow Stoltenberg presents the English, so I'll be gone for. I'll be here though 4 to 5 tomorrow, usual time. But anyway, I won't be available tomorrow night a whole lot. Okay, so saying all that, we ended up talking about what's a vector, what's a scalar, and then it came at the end of the session, there was the question of time. And what is time? Is it a vector? Is it a scalar? Now, for classical physics, Newtonian physics, time is a scalar. But then we got to talking about one of my favorite guys, and that is Sean Carroll. And Sean Carroll, let's go over here. Sean Carroll here, I got just the highlights of these discussions. We'll go over it. Sean Carroll, we talked about Sean Carroll yesterday. We talked about Sean Carroll yesterday. Okay, so here's what I want you to do. I want you to take a pencil on a piece of paper, and I want you to draw for me. I had this in class. I want you to draw for me what time does. What is time? Okay, so here is time. Let's say time is going this way. And I want you to draw for me on this line, what happens to this line that represents the idea of entropy, okay? So as you're drawing this line, it represents the idea of entropy. So I'm going left to right. I start off perfect. And then you go ahead and take it from there. I'll give you 15 seconds to sketch something on there. And I apologize if we covered this yesterday. We, in some classes, we just got to this today. So my mind, I've done it 3 times and I get mixed up as to which class did what. All right, so as you're going along, the trick here is if you're going to increase entropy, now we're saying all this because the idea is time a vector. Okay, that's where this is all this stuff came from, and then it just kind of kept going. But every once in a while, it's good just to have a free-forming discussion. So time goes along, and then as you're going, the second law of thermodynamics says that this is a very simplified version of it, is going to be greater than, I threw in the equal sign, but you cannot, in fact, that's going to confuse the issue. Let's forget that. Let's just say greater than. It's always going to be positive. There's always going to be increasing entropy, okay? So as I'm drawing this line, and entropy is the measure of chaos. How much randomness is there, okay? So as I'm drawing my line, I've got to get more random. So that thing is, once I do this, once I've got a random, now I got to get more random. You can't just keep doing this. You can't just do a sinusoid because that's not increasing randomness. So it's a little bit tricky to do this. You've got to increase the crazy, all right? You got to get a little more crazy. So we're going along and then, okay, well, I did that. Now I'm going to go up there and then I'm going to come around and it's going to do a loop. Well, now I'm doing a loop. So, oh my gosh, now it's really getting crazy. So it's got to get crazier and crazier. That's the point. How long can you draw a line and every second get a little crazier? Okay, there's a contest for you. All right, you do it on graph paper with your friends. It's a whole nother game called the Entropy Game. We'll make $1 million. And that was not a very good job, by the way. So I did some others in here, and you guys probably did better here. But there's one we did in 1 hour. That's not very good. Because I kind of changed the rules as we went. You got to get more crazy. Because that really is what entropy is saying, is things get more crazy over time. Things get more disordered over time. And then we talked yesterday, we said, well, I can bring order. If I can make my bed and all, I can clean up. Let's say I have, I have a bunch of building blocks in class. But if I put a bunch, if I throw out, what I did was I threw out a bunch of building blocks. And eventually I'll get good at this and I'll have it all set up. But I threw a bunch of building blocks out. And then it was all random. And I said, okay, entropy's high, disorder is high. So I said, okay, I'm going to make order out of it. So I built a wall, a nice, perfect wall. I said, look, I just violated the second law of thermodynamics. The second law says that everything must get more and more crazy as time goes on. And so I violated that law, right? You guys hold it. Let me see if I get the chat going. Yeah, so chat's open now if you want to ask any questions out there. But in me building that wall, I actually increased the entropy of the room because I heated it up. I made noise energy when I was banging down the blocks. So the overall randomness of the room increased. So I threw a story at them that when I was about 15, I cut the yard. And so I was hot. So I go in the house and I open the refrigerator door and I sit in front of the fridge. And my dad comes in and says, what are you doing? So, well, I cut the yard, man. I'm cooling down. And he said, what? I said, yeah, well, you should, what do you care? I mean, I'm cooling the whole house down, right? I'm opening the fridge door. Oh, it's a knucklehead 15-year-old, right? I'm cooling down the whole house. So it's good. And he said, no. So he pulls the fridge out of the wall. He has me put my hand on the compressor, and that's hot. He said, you see what it is? That makes the whole house hotter when you run this motor and you run this compressor. So inside an ice box, you do lower the entropy, but the price you pay is because it heats up the motor, all this energy. So you still end up, no matter what you do, the entropy of the universe is increased. And I'm not just sitting here saying this just for fun. This is the second law of thermodynamics. One of the objectives of high school physics is to understand the second law of thermodynamics. First law of thermodynamics, we didn't talk about it much in class. First law is EI equals EF. And we will talk about that a lot. That comes into play a lot second semester, which is conservation of energy, right? Now, as we've gone on, now it's called conservation of information because of what happens around black holes. But for classical physics, it's conservation of energy. So initial equals final. That's first law of thermo. The second law then is this, and it's much more complicated than this, but we're going to simplify it for now and say that the entropy is always going up. Okay. I'll leave. Okay. So there is something else we got to talk about. And that is another way of talking about entropy going up is, here we go. All right, how am I going to say this? Okay, so second law basically is also saying, all right, second law is also, this is something worth writing down. Second law is also saying that degrees of freedom, which is a lowercase d f, degrees of freedom, that's one way of saying it. That's what I said anyway. Degrees of freedom is always going up, of the universe is always increasing. Has to increase, okay? For time to move forward, for it to be the arrow of time, as Sean Carroll says, degrees of freedom of objects must increase. And what do I mean by that? Okay, so let's take, first of all, let's talk about the three types of motion. Okay, three types of, these are all things, I'm not just going off on this, we have to talk about this in class. So three types of motion. I didn't know it was going to come up today, but it did. So three types of motion is, one is something called translational. Translational. And that's moving from point A to point B, okay? You're translating from point A to point B. So objects, molecules, atoms in the air, water molecules in the vapor of the air can move around randomly, Brownian motion, and that's translational. So my analysis is, if you're say you're a little 7-year-old, little precocious kid, you're running around the house, you're running in the living room, your dad's trying to work, and your dad says, hey, stop running. Say, go stand in the corner. So you go and you stand in the corner. Well, he's taken away that degree of freedom. In fact, he's taken away, when he did that, he took away 3 degrees of freedom, because you could have moved north, south, or up and down. He took all those away. So you cannot, I don't want to see you jumping. I'm taking away. So he took away your translation. Well, now you're standing in the corner. And so then you start to rotate, right? Because you can still do that. He didn't take that away. And so that's another type of motion, is rotation. Now, in rotation, you can rotate in different ways, and we'll talk about that in a minute. And so he says, hey, stop rotating, stop doing that. So now you're standing there, you can't rotate, you can't move from point A to point B. So you start doing this, if you can see me. You start moving you start bouncing, not bouncing, but because you can't move your center of mass can't move in the Z direction. But this is called, as you're doing that with your arms and stuff, that's called vibrational. So those are the 3 types of motion: translation, rotation, vibration. Only 3 ways that things can rotate. And then the last thing, so what does that have to do with second law of thermodynamics? Okay, if we take water molecule, and water is H2O, so I have 2 hydrogens and an oxygen up here, 105-degree bend. And really, these are more like springs. There's nothing there at all. It's electromagnetism, right? It's a covalent bond. But I'll make them springs. And then if I'm going to translate, okay, the water molecule is translating around the room. That's H2O. It's called, you'll see it written in chemistry as H2OV, right? H2O vapor. So it theoretically is detached from other water molecules. I mean, it attaches to things like dust particles and stuff. But let's say it is a free-flowing water molecule. Now the question is, how many degrees of freedom does that water molecule have? And what that means in its motion, how many ways can that water molecule that's bouncing all around your room, all around your head right now, how many ways can it possibly move? And those are called degrees of freedom. Well, if we said that translationally, if it's bouncing around the room, it can go X, Y, or Z, right? So we'll keep track here. That is 3 translational, 3 degrees of freedom translational for a water molecule. Well, a water molecule can rotate too. And to rotate, you first have to find the axis of rotation. And that is a line of symmetry in that molecule. And the things rotate around their lines of symmetry, okay? So the water molecule can rotate like some kind of a game, some kind of a carnival ride, rotate around and around. And so that is another degree of freedom. Now, you might be able to pull a couple more lines of symmetry out of that. I heard that water molecules barrel roll, but let's just go with that for now. And finally, how can water molecules vibrate? Well, if these are springs, this spring can stretch. And so this H2O, both springs can stretch at the same time. They can flap their wings a little bit. They can, what else can you do? You can flap the wings the other directions. But we ended up getting about 3 today. We were thinking about it. So that's a total of 7 degrees of freedom for a water molecule floating around the room. All right. We're talking about entropy, remember? So what we're saying is every object in the room will tend towards maximizing its degrees of freedom over time. That is how time progresses. This thing, that time is a measure of how much disorder there is in the universe. Okay, so every second that goes by, there's more disorder, more degrees of freedom. Now, there's something called dark energy, which is trying to maximize degrees of freedom. So you might think that the universe. Now, this is me. Okay, I've thought I say this, and so don't look for this in a book, but it seems correct, right? The universe then tends to maximize degrees of freedom. And what is running that show is dark energy, right? That's what's causing everything to separate as much as possible. So when you think about it, dark energy, all dark energy wants is for you to have your freedom. Okay. And if you get morbid about it, I think when you die, I mean, your particles, your atoms are all becoming more free. So you're increasing your degrees of freedom of the universe. Okay. So, think of it this way, then think of entropy as this tendency to maximize chaos, but sometimes that word chaos doesn't make much sense. So a tendency to maximize degrees of freedom, if dark energy then pulls you apart eventually, pulls your left arm from your right arm, pulls your molecules apart, pulls your atoms out of the molecules, then goes in and pulls the protons and neutrons apart, then goes in and pulls the quarks apart. Every time you do that, you're increasing degrees of freedom. See, so the universe, the idea originally was that back when I was in high school, there would be a big crunch. Like right now, there's a big bang. And then it would eventually, gravity went out and it would become a big crunch. And in that case, time would go backwards, by the way, because entropy would be the opposite. Things would get more and more ordered over time, which is a little nutty for us to think about. But what that's saying, what the prevailing idea is that dark energy is going to win, and so we'll end up dying in what's called I wrote it here somewhere. We end up dying in what's called a heat death. If I had it somewhere, anyway, a heat death. Everything's going to die in a here it is. Everything's going to die in a heat death. Okay, as we maximize freedom. Okay, so it's all about freedom, baby. But that will end up the universe in a heat death. Okay, total chaos. Entropy wins. And we ain't coming back. There ain't going to be no big crunch. Okay, so that's enough of that. We talked about it. What I promise you is anytime and that's not going off because we had to talk about that this year sometime. So it just came out today. So anytime we have a crazy discussion in class, I'll try and recreate it here. It's a little harder when I'm staring at a bunch of names, but and feel free to jump in there. You can say something. Sometimes it's easier just to chat. If you want to time, I'm reading the chat here. So far, just Jacob said hi. Okay, so now let's go. Let's knock this out, and then we'll be done. All we're gonna do today is do this little bit, okay, on vectors. So let's get to something easier. All right, how about this? It's something beside easier than all this dark energy and stuff. How about this? 3 plus 4. 3 plus 4. What does that equal? Of course, right? Of course, 3 plus 4 equals 7. Actually, there's about, I'm going to say that's maybe, there's a chance. There's a chance that it equals 7. But there's a much greater chance it equals something else. okay? And actually 3 plus 4 can equal anything from, it has a range of answers. It can equal anything from 1 to 7. It can be 1 to 7. It could be 2. It could be 3. See, we were lying to you. We've been lying to you on this. Well, for scalars, it's true. I mean, if I have $3 in my left pocket and $4 in my right pocket, I got $7. I'm not arguing that with you. But I'm saying that if you're talking vectors, that's probably not true. And I don't have arrows here. I have arrows in class. I got to start bringing props home. If I have 2 arrows, okay, let's draw it. So if I have 2 arrows and one arrow has a length of 3 meters, whatever, and one arrow has a length of 4, and I line them up head to tail in a same line linearly, then I agree. The resultant, which means you add them both up, the resultant always goes from the first tail to the last head. And by the way, on vectors, I don't have my props here, but on vectors, this is the head, and this is the tail. And back, I'm sure how old I am. Back in the physics, the Resnick physics book that I had, I think like the 2nd edition. Now it's probably like 12th edition or something. But back then, they actually drew feathers on vectors. A lot of vectors have feathers, and this was the tail. So here I am adding these 2 vectors up. This is going to become very important here in a minute. I'm adding these 2 vectors up head to tail. Okay. The resultant goes from the very beginning to the very end. So in this case, the result is going to overlap those 2. And the resultant, I always make my resultants in red or at least a different color. So the resultant here is R, and that is equal to 7. Let's say we're in physics. We should have meters. We should have units, right? So 7 meters. All right. Could be meters per second, by the way. Anything you can represent with a vector, it could be 7 newtons, okay? Anything you represent a vector could be the units there. But that's only one case. Now, can somebody show me, or they can't really show me, I need to be able to annotate on this thing. Hold on a minute. Let's add annotation. Annotate. Can you guys annotate? Can you annotate on here? Hold on. Disable enter. No, I didn't disable it. You should be able to draw on your trackpad. Maybe. Oh, Jacob did. Okay, Jacob put an arrow there. A little more student participation here. I should hide name of animators. No, I want your name on there, if you don't mind. All right, so Jacob's got an arrow pointing to something. He's playing around with it. So try on your trackpad, Jacob, or your mouse. That's me drawing. Now you try and draw something. Let's see if you can draw on there. I'll take my hand away. See if you can take over the screen. Can anybody take over my screen? I didn't disable it for you. Because I know in June, well, no, in April we were doing this. The kids were annotating stuff. Jacob says, oh, Sophia's saying, how do you do it? Oh, Sophia just did it. And Jacob's saying there is a view option button on the top, which brings a drop-down menu, and annotate is one, right? So yeah, I have that. I mean, I clicked on the annotate button, and I have all my tools here, but I've disabled the thing where it says, okay, now Evan's in there too. So I've said, let you guys animate. So this will be our whiteboard here, and now I'm doing it. Oops. It's gonna get tricky here. Okay, so let me move the chat out the way. Okay, so what I want you to annotate, now that we're starting to figure out how to annotate, what I want you to annotate is, I want you to show me, draw for me on our whiteboard, how can you possibly say that 3 plus 4 equals 5? Show me 3 plus 4 equals 5. You got to get good with your fingers, right? If you have if you're watching me on an iPad, you might be able just to use the iPad to do it with. I don't know. All right, so Jacob's taking up the challenge. He's got a 3-meter vector, okay? Now he's going to draw a 4-meter vector. It's hard to do. It's like you're back in 2nd grade, you know, trying to write with your finger. Okay, so that's a 4-meter vector. I got you. And then Jake, I think only one person can do it at a time, right? So, okay, good. Okay, I see what you did, Jacob. You did an overlap there. Nice. Okay, not legal, but nice. I like the way you think, man. So you're saying, well, the heck with that. I'm going to add up 2 vectors. I'm going to say, well, that's 3. No one's ever done that, by the way, in my 20 years of teaching physics. Since I've been 99 on physics anyway. So he said, well, just do it like this, something like that. Just overlap it. They can't overlap. It must be this guy. Okay, if this is great stuff, man. This is great stuff. I love it. If this is 3, the 4 vector, if that's 3 meters, let's say, the 4-meter vector, its tail has to touch the head of the 3-meter vector. So they can't overlap. So I can put that 4-meter vector, if I do it in black, I can put it like this, any angle I want, 4 meters. I could put it like this, any angle. So if that's, but they do have to go head to tail though. All right. But I want 3 plus 4 to equal 5. Now this also, by the way, will help you on the ACT if that's a hint. 3 plus 4 has to equal 5. Okay. Anybody else want to give it a try? You can also throw your, okay. Takaki's going to jump in there. He's got 1 vector going. That's a line segment. I get it. It's an arrow. We get it. Okay. So he's got an arrow. Oh, okay. Put another arrow on there. All right. So one of them is 3, I guess. Okay. So he said this. He said, just do it like this. Come on, man. This is a better discussion we had in class, actually. What we're having right now. I think I come up across a better way of saying this. Okay, so that's 3 meters. Takaki said, well, I'm going to make that 4, and I'll put it at an angle like this. That's 4. And then he said, well, I'm going to guess that maybe that's 5. Maybe that's 5 right there. He's on the right track. On the right track. Oh, yeah, so what he did was, on the annotation, he actually just drew the line, just added the lines. It's pretty good. That's not quite right. So that's still a big no. And here's where, okay, let's go ahead and talk about it then. I'm trying to get you out of here. So if 3 looks like this and 4 looks like this, then, and that's a right angle. You guys ever heard of a Pythagorean trio? Oh, I can't really see it. Pythagorean theorem, right? Pythagorean trio, 3, 4, 5, right? There's a, what is there? A 5, 12, 13. And there's one more involving 20, 21, something. These are the Pythagorean trios. So if that is 3 and that is 4, the hypotenuse, which is the resultant vector, the hypotenuse is 5. 5. So that's an example of a vector being 3 plus 4 equals 5, because that's your 2 vectors that add up, and then 5 is the resultant. We call the resultant, we give that an R and put an arrow above it. I would call this like you put an arrow above the symbol to represent that it's a vector. Okay, not just a scalar. Now, you should do it every time, but nobody does. We all get tired of it after a while, but I will try and be a good boy for a little while and put arrows above letters, and then I will pretty quickly get grow tired of that. But you're supposed to. Okay. So if in Takaki's case, I think he was onto something, but I would say in that case, probably 3 plus 4 equals 6, equals 6 meters. Okay, in that case. Just do one more since we're having so much fun. Do 3 plus 4 equals 2. Try to show me, and I make you do these on tests, not this, well, could be this test, I guess. 3 plus 4 equals 2. Show me that on a drawing. Well, or just do it on your paper, and then if you feel brave enough, try and annotate it. First, do it on your paper, because this annotation, I must say, is pretty unforgiving. 3 plus 4 equals 2. Okay, you have your choice, you have your guess. All right. 3 plus 4 equals 2. All right, so I have one that's 3, my 3 meter one. This time, that's 3 meters. This time, my blue 4 meters has got to come back. Maybe like that. Maybe that's my 4 meters. And then my 2 meters, my resultant, goes from the very beginning to the very end. So that would be my 2 meters. Okay? So that's what I'm talking about. Vector world gets strange, but it's really the world you live in. All forces are vectors. All velocities vector, all accelerations are vector, all displacements are vectors. So you can't get away from it, right? All right, so there's that. And now I want to go back and let's try and knock this off. Okay, so here I'm showing you adding up 2 vectors, A plus B. So the resultant then is, I'll make a different color, and I'm showing you the resultant going from the first tail to the last head. I said you always have to go head to tail, and then today an observant student said, well, Mr. Askey, looks like you made a mistake. If you're always going head to tail, why did you just go right here? Why did you just go head to head? The resultant goes from the first tail to the last head. You wonder why I make half arrows? That's why I make half arrows. I couldn't get a half arrow in the computer. But so like when 2 vectors come together, you need 2 half arrows. See that right there? The blue and the red, so they don't overlap. That's why you do half arrows. All right, let's do this, and then we'll call her good. Now I made them go to the board, not on this one. Let's do this one together. Oh, I see. I'm going to have to. Let me see if I can kill the annotations here. Clear. Clear all drawings. Good. Okay. So it does get in the way after a while. Okay. So you can keep drawing. I'll just clear them if I have to. All right. So this time you have to redraw. So we're going to draw the resultant of these 2 vectors. I don't care whether they're force or could be anything, but they're 2 vectors. And we need to add these up and then draw the resultant. So you have got to redraw one, pick one, leave one alone, redraw the other one, and then connect it. Okay, so I'm going to go ahead and redraw. I'll redraw the one at an angle. Okay, I'm going to cheat. You can't cheat, but I'm going to cheat. I'm going to use a little cutout. I'm going to copy this with the iPad, cheater, and then I'm going to move it. See, this is the probably I'll be teaching it this method, right, in 5 or 6 years, because everybody have iPads, and so you got to do that. You have to do it. Drawing it though, you have to redraw it. I don't want to see old shaky hands come around. You have to redraw it carefully. So these are called construct. When it says construct on a test, you have to use rulers and preferably protractors. All right, so then we don't need a protractor on this one. And then we draw the resultant. Now the resultant goes from the very beginning to the very end. So the resultant goes from, I promise you, we're getting almost done here. The resultant goes, you guys are doing amazing being here on a Wednesday night at 9 o'clock. The resultant goes from the beginning to the end. There you go. Draw it in a different color. Show it like this. Okay, now I want you to do, the last thing we're going to do is I want you to do this one. I want you to add those 3 vectors up, head to tail. Now, I made them go to the board. You can do it on your paper. It'd be kind of cool if you could like send a picture, like take a picture of your work and put it in the chat. I don't think that I can do that. How can we do? You could hold it up to the screen, I guess. You could hold, you could do it and then hold your up to, you could turn your camera on, hold it up to the camera. I don't like cameras on when we're doing this. So if you do that, kind of cover your face. But I'd like to see you try this. Okay. So we have vector. So we have vector. You keep working. I'm just talking here. We have vector A, B, and C. And our equation is A plus B plus C equals R. Change colors here. So we're just trying to show the resultant of these 3 vectors added up. It could be 3 forces, and you're saying, what's my combination of my forces? Okay, it's called the sum of the forces. Okay, so you now, okay, I'll do it like I'm supposed to do it. I'm being lazy, but let me do it like I'm supposed to do it. So instead of, I can't just cut things out in real life. So here we go. You do it, but listen to me as I go. No. Okay. I want to blow it up though. That's the problem. Okay. So I've done it. I'm going to leave A alone. I'm going to move B and I'm going to move C. So the first thing you do if you're going to move something is you draw a line of action. So for C, so B, the line of action, remember that's that dashed line that goes on forever and ever. In fact, sometimes I'm doing this mindlessly if I'm on paper, and I just draw, here's C's line of action. Okay. Okay, it goes on forever and ever. Now you're using this as a visual. So when you're redrawing it, you keep it, I'm trying to get it so you don't have to use a protractor. Okay. Okay. I'm going to redraw B. Now these are called ghosts. What I'm drawing are called ghosts. They're not the actual vector, they're ghosts. I'll make my ghosts, let's make my ghosts orange. Okay. So there's orange like Halloween, right? So I'm going to redraw my ghost. So I get the length of B correct. 1, 2, 3 ticks here on my thing. And notice these are parallel, my railroad tracks. 1, 2, 3. Okay. That is B redrawn. I made them do this at the board. They weren't liking it too much. So it's a little bit off, but that's my head. My head of A is at my tail of B. Then now I'm going to redraw C and put C's tail at B's head. All right. What are you doing, Asking? Something you made up? No, I didn't make this up. 1, 2, 3, 4, 5, 6, 7 for me. So I'm redrawing C now, parallel to C. And I'll make my ghost in this color. So 1, 2, 3, 4, 5, 6, 7. Ghosts, a student teacher of mine, Ray, came up with this one, Ray Kippham. She's now a physics teacher out in Seattle, doing really well out there. I liked it so much, I've still used it. Her idea, her name of ghost. I don't know if she still does use it or not. And then the resultant goes from the very beginning to the very end. So my resultant goes from the first tail to the last head, R. Now, like I say, this is not just doing this for funsies. This is all of next semester. Is working with vectors, and it's also some of your second semester of pre-calc is working with vectors. You don't know it sometimes you're working with vectors, but you are. Like you do dot products and cross products. That's all vector stuff. Okay, and there's my R. So my R is, that's it. That's why we didn't say to do anything else, just said to draw it. So I think that's a good time. We're at 51 minutes. It's late. We're all bushed. If you want to look ahead, the only hour they got to this, I think, was second hour. And we just got started on that stuff. So let's not worry about it. Tomorrow, we have to take a break because we're going to the stadium. So I don't know if we'll get much on this tomorrow. I doubt it. We'll probably postpone this till Friday to continue on talking about it. I wouldn't go to the stadium tomorrow, except that that's the best weather day. So hold on, let me stop sharing. Hello, everybody. So that is our best weather day. Hey, can you tell me if I'm on the screen? I know I've asked this before, but can you see me? Can you see
Yes.
my face?
Yes.
Okay, because when I can't when I do it. I mean, when I'm watching the recording, I don't see me. So that's too bad. I mean, sometimes I'm doing this and I'm doing this, and anyway, oh well. The live people can see it, but the recorded version can't. It's too bad. Okay, I think I'm going to stop recording.
And Mr.
Anybody got any physics questions? All right, given. Yeah, I heard the news. It was horrible today. Starship went down, blew up. I didn't see it. I was busy, but yeah, SpaceX had a major problem today. System failure.
On my test,
Yep.
I didn't finish a couple problems on the bottom, and so I wrote, I need more time. But
I know. See, here's the deal, though. I agree, but you got to give that test to me, so I put it in the box. I put it in my drawer. Um, we'll talk about it more later. Um, yeah. See, now the key's out. So, yeah, we'll talk about it more later. But if it's a situation like that, you can give it to me at the end of an hour. But we'll talk about that. You're not going to talk about that more tomorrow. Okay.
Okay.
But did you see the explosion, Gibbon?
Yeah, I watched it live.
Oh my God! You watched the whole thing. Did you watch it till the explosion?
Yeah.
Oh my gosh, that must have been something, huh? I wish I hadn't seen it live because it turned my stomach. But man,
Well, they learned a lot from it.
they learn a lot, and it's a test. It was a test flight. You're supposed to learn from test flights. People go freak out. It's a lot of money, but they did. I'm sure they will learn a lot, and that won't happen again.
Yeah.
A lot of rockets blow up. Okay, let me stop this.